Okay, right, so before I show you what's inside, let's quickly have a look at the rating of this thing. This is a 14.4 volt, 73 watt hour battery. So firstly, let's figure out what that, so 73 watt hours, again, that is a more useful capacity measurement. Let's just convert that into milliamp hours so we can compare it to the other cells that we've been looking at. So to do that, we do 73 divided by 14.4. which gives us 5. So we're expecting this to be a 14.4 volt 5 amp hour battery, or thereabouts. Now the thing is, you'll also notice that 14.4 isn't divisible by 3.7, so there's going to be a little bit of electronics work going on in here, adjusting that voltage for what the laptop wants. So here's what we've got inside. As you can see, it's a bunch of 18650s. 18650. So this is a very common arrangement inside a battery where they've basically just crammed in as many 18650s as they can. So now let's figure out how these things are wired up. So 14.4, the nearest thing we have to that is 14.8 volts. That's the nearest divisor to 3.7. So what we probably have here is a 4-cell battery. So 1, 2, 3, 4. So that's 3.7 times 4, giving us 14.8, and then this battery controller down here is probably stepping that down slightly to 14.4 to give a steady output even when the battery is low. Right, and if we look at the end of the battery, you can immediately see they're all in a row, so negatives on the left, positives on the right. So these positive pins, these are parallel together. We've got 2 positives that are parallel together, and at the back end we've got 2 negatives that are parallel together. And if we just gently bend that open, as you can see, we've got 2 positives that are then wired into 2 negatives. So it's literally what I predicted. We've got 4 pairs of cells. So these 2 are in parallel, these 2 are in parallel, these 2 are in parallel, and these 2 are in parallel. Then the whole lot is in series to create the total battery. So these are being combined to build up the capacity of the battery, and then the pairs are being combined in series to build up the voltage of the battery. And if we take one of these out, we'll find that each one of these on its own is 3.7 volts. No idea what the capacity of each one might be, but we can probably take a guess. Right, my numbers while recording this segment were completely wrong, so here comes the voiceover. Before we go any further, we have to allow for the fact that once we take the voltage from 14.4 output up to 14.8 for the battery voltage, that will change the capacity calculation, because you can't change the voltage without changing the amps. And I'll show you how we do these calculations later on. However, first of all, once we adjust 14.4 volts to 14.8 volts, the capacity of the battery will go down to 4,864 milliamp hours, because the voltage goes up, therefore the milliamp hours have to go down. So we have 48, we'll call it 4,800 milliamp hours total capacity. Now, because we have a 4-cell battery, we're combining the voltage from the individual cells, so we only actually have 2 cells creating our capacity, which are those pairs. And if we divide our capacity by 2, we get 2400. So we're expecting to see approximately 2400 milliamp hours in each one of the cells. But as you can see, it's actually very basic. And then over on this controller, what we'll find is we have some current sensing circuitry here. We have a 0.1 ohm resistor with some traces coming off of it, so the controller can detect how much current is flowing through the battery. And then we've got a couple of controllers here. These will be controlling the input and output from the battery, and we have some MOSFETs here that switch the current. So one of these is probably handling the charging of the battery, and one of them is probably handling the discharge of the battery. So the discharge will be stepping the voltage from 14.8 down to 14.4 volts on the output, and then the other one will be receiving power from the laptop and then charging the cells up. And if you have a look, you'll notice we've actually got some little traces going around this thing. And if we follow those from the control board, you can see we've got little spots there on the control board. And what we'll find is we have a small trace of wire. Well, actually, this trace is going to a thermal sensor, but these traces here, each one is going to the individual pairs. So the controller can sense the voltage in each pair of batteries and make sure that they are balanced. And that will make sure that if one of the pairs is slightly overly discharged, it can individually just nudge the voltage up on that pair to bring the whole total voltage of the battery back to where it should be. And I could also open up this MacBook Pro battery, but here's one I opened earlier and stole some cells from. The MacBook Pro battery I opened up, it was a cheap and cheerful one, and it contained 9 of these flat cells. As I mentioned, I've removed some of them. It had them. I'm going to turn those over just in case I short them out. It had them built up. Oh, I don't know where the other one's gone. We had 8 of them and a 9th on the end there, and that was creating a 4-cell battery with 3 cells in each of the battery cells. So they had 3 of these in parallel and then 4 sets of 3 to create the 9 cells total. And again, as you can see the wiring on this one is very clear. On these we have 2 triples remaining. So we've got these 2 cells on the end. These are wired directly together, and then it's got 2 jumper wires, this one and this one, that go over to this cell. And then once again, these 2 here, these are wired directly together, tab to tab, and they've got 2 jumper wires going over to this cell. So there's the triple, 1, 2, 3, 1, 2, 3. And then finally, we've got a negative coming off of the end of the entire set, and we have a positive that jumps over between the 2 triples. And we have the same thing on this end of the battery, where we had another triple set that once again was wired onto the end. And this blue wire, this is a sense wire going to one of the center triples to make sure that the controller could detect the voltage in the middle of the battery, as well as at the top and the bottom. So that's how laptop batteries are built. Now, quite often when a battery has failed, especially like a laptop battery, it's quite often because the controller has died, or sometimes just one of the cells has died and is dragging down the whole battery. And more often than not, there will be plenty of cells inside the battery that are still perfectly healthy and reusable. So if you want to mess about with electronics and powering things off of batteries, old laptop batteries are a great place to scavenge secondhand cells from and reuse them. So let's continue down the rabbit hole of this particular battery and see what we can get that is usable from it. So what we'll do, I'll just take you in a little bit closer, and we'll rob one of the cells out of this thing and see if we can put it to use. So let's start from the end here because it's quite accessible here. So I'm going to desolder that tab, and then we'll just chop that tab off there and we'll have one of the pairs. So I'm just going to warm up my soldering iron. And while we wait for that to warm up, we can just have a look and see what the general health of this thing is at the moment by turning on my multimeter. And we'll stick the black onto the negatives at the end. And if we just touch the middle point there, where the cells join up, oh, that doesn't look promising. We've got nothing at all. Oh dear. Well, these things look like they're stone dead. Oh, there's something. We've got 9.5 at the end of the battery. Where does that power start? 2.4. So this cell here is at 2.4, which is very under power, but there's some life there. What about in the middle? There's another 2.3. Did I just have bad contacts there? 3.2. Oh, okay, no, I think I just had bad contacts then. And 1.4, yeah, I just had some bad contacts there. However, this one's down at 1.4 volts. So these things, they're completely out of balance because we've got 2.4 up here and 1.4 down here, and they're all critically under power. You don't really want a LiPo cell to drop below 3 volts. That's kind of the critical marker, and most battery controllers will usually turn off at 3.2 volts or maybe even 3.4 volts. So really, these things are all critically low. But if we put some charge into them, we can probably recover them, and I'll show you how to do that in just a moment. So now, let's try and split these off into individual batteries. So I'm going to grab a pair of pliers, and the most basic way of removing these are spot welded, because technically you don't really want to apply heat directly to the battery. You can get away with it if you're quick though. However, for mass manufacturing, they spot weld them. And if you grab a pair of pliers, you can usually just tear spot welds off. So I'm just going to open this. Damn it. That didn't go very well. I'm going to try and open this like a tin can. Let's just pry that end up. And I'm going to be a little bit more careful this time. God, these are good welds, these. Normally this kind of brutality will take those off. But you know what? Because I'm recording a video, I'm not going to fret over having a tiny little bit stuck on the end there, so we'll leave that alone. And now we just left a tiny little bit on the end there, so I'm just going to scrub that off with a scraper. There we go. We've got a nice flat end there, and we've got a few bumps there, but that'll be all right. Okay, so now we've got a recovered 18650 cell that we believe to be about 1.2 amp hours. Now, theoretically, I could probably look up that model number and find out. So SE Sanyo Electronics, maybe. Let's Google search that number. It's a Sony. Well, that's interesting. So according to its datasheet, this thing is apparently a 2 amp hour cell. So I may have been wrong on my calculations there. But then on the other hand, we were calculating from the output voltage, from the 14.4 output voltage. And because we're calculating from a different voltage, the actual capacities can be squicky. And this is exactly why milliamp hours isn't a very good measurement of the battery, of the cell power. So let's work on the datasheet. So theoretically, these things are apparently 2 amp hours, and that's not bad. That's not bad going at all. So what we'll do is we'll try and charge this thing up. So I'm going to grab an 18650 battery holder here. And we'll put that in there. And let's see what we can do with it. So that guy's at 1.4 volts. So this thing is super low, but it's still above 1 volt. Even if, to be honest, even if it had gone down to 0, I would attempt to charge it. However, when you've got a battery when you've got a cell, I've slipped into using battery just like I said I would. When you've got a cell that's gone drastically under voltage, you need to be careful when charging it. We're going to start charging it at a very, very low rate to just slowly nudge the voltage back into the acceptable range. And then once it's operating in its correct range again, then we'll give it the beans and actually put some energy into it. So let's get this thing on charge, and I'll show you how you can charge it up either with a proper LiPo charger or just from a bench power supply. So the first method of charging this LiPo cell that I'm going to show you is using a bench power supply like the one I've got down here. So this is a very good way of demonstrating how LiPo cells charge up, because it's a 2-stage process. The first thing that we do is we have to bring the voltage of the cell up to 4.2 volts. So while we do that, we're going to regulate the current, because as we apply power to the cell, it will try and soak up as many amps as it can take. So if we don't regulate the current, it will just go almost dead short kind of thing, and it will just spontaneously combust itself. So we're going to regulate the current. Now, this cell, according to the data sheet, wants to be charged at 1 amp. And that sounds kind of low to me because allegedly it's a 2 amp hour cell, and usually most cells are happy with at least a 1C charge rate. So if it's a 2 amp hour cell, you can charge it at 2 amps. However, 1 amp is fine for a charge speed, especially on a smaller cell like this. On big cells, 1 amp is going to be a bit agonizingly slow. However, for just a single 18650 like this, 1 amp is fine. We're not in a hurry. So we're going to regulate it at 1 amp, and it's going to soak up 1 amp until the voltage reaches 4.2. When the volts reach 4.2, the power supply will regulate to 4.2 volts. So it'll switch from regulated current to regulated voltage, and then we'll see the current slowly tail off as the battery finishes charging. So we've got our voltage on display down here. We'll also see it from the power supply, although the power supply will show us a slightly increased value. My power supply here is not particularly accurate, so please forgive it. So firstly, I'm going to set up my power supply. So let me quickly disconnect the leads from the LiPo cell. So I can't remember what I set this to. Right, let's turn that on. Yeah, we're on 12 volts. We don't want that. So we're going to set our power supply to 4.2 volts. And because we don't want to brutalize this cell, we don't want to go all the way to 4.2. We want to go to just under that. So I'm going to turn down the voltage now until we drop to just under 4.2. Don't ever buy a power supply like these ones. They're crap if you need precision. There we go. So I've just nudged it just under 4.2 volts. We don't need 100% here. 98, 99% capacity is absolutely fine. So we're at 4.1 something volts. And now let's regulate the amps. So I'm going to set my amps down to 1 amp. Right, and that would now be ready to go. However, the other thing as well is that our cell is currently dangerously under power. We're down at 1.2 volts. So what I'm actually going to do is we don't want to belt it with an amp while it's already feeling a bit poorly. So I'm going to bring my amps down to about 100 milliamps. I'm going to take that right down. So that way we're just going to trickle charge this cell until the voltage recovers. And once the voltage recovers up to about, once we're over 3 volts and it looks happy, then we'll give it the beans and take it up to an amp. So let's hook up the cell. All right, there we go. So we're now charging. And as you can see, the cell voltage is jumping up very quickly. That's faster than I expected it to. Oh, my thing is complaining because it's been idling. There we go. So I'm just going to let that charge. Oh, there we go. That's settled at 2.5. So I'm going to let that come up to 3 volts now. And when that hits 3 volts, we'll take it off charge and we'll just watch the voltage and see how much it sags. If it's holding that voltage, we know that the cell is still okay. Whereas if we take it off charge and the cell voltage just plummets back down to 1 volt, then we know that the cell is completely toasted. Okay, so that's up to 3 volts now. So what I'm going to do is I'm going to disconnect the positive lead here, and let's just watch and see what the cell settles down to. The voltage will drop because it always does. The cell will just settle, but I just want to see if it actually crashes down in voltage or whether it just settles down to a decent rate. Alright, and after just under a minute or so, It's slowly drooping, but that's not exactly crashing down at all. And bearing in mind, we were only putting 100 milliamps into it. We haven't given it much at all, but it's still holding just under 3 volts quite happily. So it looks like this cell is absolutely fine. It just needs a good charge. So I'm going to plug that back in. Let's get a good connection there. There we go. And now I'm going to give it the beans. So I'm going to up the amperage up to an amp, and we'll start putting that on proper charge. And as you can see, as I turn up the amps, it's just sucking up whatever amps I give it. And now the voltage is soaring because it's actually getting a lot of power. And so now we're just going to let that run, and this will build up the cell voltage until the cell voltage hits just under 4.2, because that's what we set the power supply to. And once it hits the voltage set on the power supply will automatically switch from control current to control voltage. And you'll see this red light turn off and the green light come on. So I'll point that out when we're coming up to that point. And we'll see it switch over into the second phase of charging. Okay, right, so we clicked over to control voltage. However, it looks like my power supply was set a little bit low, because as you can see, our cell is only sitting at about 4 volts. So I'm just going to nudge the voltage up a bit more. I'm just going to take that up to 4.2 indicated. So no, that still wants to sit on control voltage, but that's fine with me. The cell voltage will still go up a little bit higher as it takes on power. So that's completely fine. Now you'll notice that we haven't changed the amperage, but the current has now dropped down to 800 milliamps, and we'll see that slowly tail off as the cell continues to charge. We're in the second stage now, and once the cell has taken on as much charge as it can, we'll probably see that the cell voltage will nudge up to about 4.2 or so. So that will slowly continue to climb. However, we're mainly now just soaking up the last of the amperage. So we'll watch that run, and you'll see that the current just slowly backs off as it continues to charge. So we've been on charge for nearly about 3/4 of an hour now, and as you can see, we're still slowly nudging up the cell voltage, and the amperage is still slowly dropping down. But it's taking a while because now at this point the battery is just still soaking up that power. And this is the interesting thing about fast charging, because obviously I can't make this go any faster now. I can turn the amps on the power supply, I can take that dial and whack it up to full. I can turn that guy up to the stops. It's not going to charge it any faster because the cell is already at its high voltage, and it will sit there and it will only take on as many amps as it wants to. So at this point, fast charging doesn't help you because we're still limited. Oops, I think I just nudged the voltage. Yeah. Anyway, so the point is, it's only going to take on as many amps as it wants, and we just have to be patient and just sit and let that slowly soak up the amps. But eventually, those amps will tail off to nothing. And when it gets down to about, 100 or 200 milliamps, at that point, we've more or less had our money's worth, and it's charging so slowly that we're not really getting anything out of it anymore. So I'll leave this thing on charge until the current drops to, because it's only a small battery, I'm going to let it run down to 100 milliamps, and then we'll switch it off. Right, so this has been left to run now. I left it on for quite a while. As you can see, we've dropped all the way down to 90 milliamps, which is, this cell is full now. Basically, we've had our money's worth out of it. So I don't recommend running it any longer than this. It's not going to do it any real harm, because where we're limiting the voltage at the cell, it can't take on any more power than we're giving it, and basically the cell is reaching an equilibrium with the power supply. However, by the same token, there's no real benefit to charging any further than this, because you're not getting a useful amount of power into the cell. And in addition to that, this does not necessarily mean that you can just leave it running overnight. I don't recommend charging a cell unattended in this manner. I doubt anything bad will happen, but it's not really a good idea. Whereas other chargers, proper LiPo chargers, will automatically turn off when they drop down to a certain amount. Like, a lot of them will automatically switch off at about 100 milliamps or less. They'll just auto cut the power. So because they automatically switch off, it's quite safe to leave them unattended. However, this power supply will just keep dishing up power until an equilibrium is met. And yeah, as I say, we don't really want to reach that point. We're just going to brutalize the cell. So let's take it off charge. And we will find that we have a nice steady 4.2 volts there. There we go. And because I actually left it on for a little bit too long, we're actually a bit hot there. We've got 4.24. So this cell is really crammed full. Truth be told, I did actually leave this cell unattended. I didn't leave it overnight, but it did actually run for a lot longer than I intended it to. So we've crammed this thing chock full. So now it's time to discharge it and see how much power we get out of it. So we'll see how much useful power we get out, and that will let us know what the current capacity of this cell is. So if you don't have a bench power supply, or if you want something a bit more practical than that, which is completely understandable, your other option is to jump on eBay and buy yourself a very cheap power bank. So a power bank like this one, this can be purchased on eBay for about £1, and it might have a really crap 18650 in it, or it might just be an empty one. I bought this one with no cell in it, and it cost £1. And this has just a very simple circuit board in it that has a LiPo charge chip on it that will do the same current and voltage regulation that I was doing with the bench power supply. And it also has a 5-volt boost circuit in it. So when it's powering the USB port, it boosts the cell voltage from that nominal 3.7 up to 5 volts for the USB output. So a power bank controller board like this is the most practical way that you can put a LiPo cell to use, especially if it's a recovered one. So this particular one is designed to take an 18650, as you can see. I've just got some jumper wires on here so I can plug other cells into it. That's what that's all about. So what we can also do is take one of my recovered cells, pop it in there, and just simply plug it into a mobile phone charger, and that will charge the cell up. And what I can also do is, because we now have USB ports on this, this makes it a lot easier for me to measure the amount of power that's being used here. So I can take a USB energy meter like this one. These can be purchased for about £5, and if I just plug that in, oh, this is a flat cell, that's not going to get me far. Let me just put in something that's not flat. So if I plug that in, as you can see, it's now showing me the 5-volt output, and it will show me the power draw. So I'm just going to plug in a dummy load here. This is an electronic load, and again, you can buy these on eBay. And so we've now put an 800 milliamp load onto this thing, and we're now powering this dummy load, which is just literally, it just burns electricity as heat. So we're now drawing power from the battery. So we're drawing the battery voltage, which then gets boosted up to 5 volts to power this thing. Now, because this measures milliamp hours that flow through it, we can now measure the capacity of the battery. So once I've charged up my recovered cell, I can then put this arrangement on it, and I can run it until the battery is flat, and I can record how many milliamp hours came out of the battery. And that allows me to measure the capacity of the battery. So let's run that test with one of my recovered cells. I'll put the recovered cell into this guy, I'll charge it up until it says it's full, and then we'll discharge it and see how much power we get back out of the cell again. Right, and there we go. We're at the last dying breaths of this cell now. As you can see, we're starting to drop heavily. The voltage is starting to tank now. We're about to hit 3 volts, and I think that's where it's going to cut out. And we're going to hit about 900 on the dot, I think. So I'm actually going to wait and watch for that, because I'm curious as to see what the cutoff of this thing is. No, it's dropped further than that. So it looks like this is actually going to take it down even lower. There it goes. So allowing for inaccuracies, that dropped out at 3 volts basically. However, my multimeter is probably more accurate than that is. So there it is. Okay, so that was it. And I'm just going to hot plug that one more time just to turn it on. Yeah, 895 milliamp hours. I'm calling that 900. That's good enough. Because we can now run this for a little bit further. If I just come off of max min there. However, you can see that the voltage is tanking again. We've definitely had a lot from it. Cool. Okay, so we also have to remember that because we increased the voltage from a nominal 3.7 up to 5 volts for the USB voltage, that will have lowered our milliamp hours, because if the voltage goes up, the amperage has to go down. So how do we calculate what was actually in the cell, not what came out of the USB port? Because when you buy a power bank, the advertised capacity is the capacity of its battery, not how much actually comes out of the port. So in order to figure this out, we take how much we got out of the port, which was 900 milliamp hours, and we times it by the output voltage, which is 5. Then we divide that by the cell voltage, which in this case was 3.7, because we have a single cell. And that gives us about 1200, or 1216 to be precise. So we actually had about 1200 milliamp hours in the cell, and then after that got boosted up to 5 volts, it dropped down to 900. So we've got 1200 milliamp hours. So when all was said and done, we were looking to get about 2 amp hours out of this cell, but we only got about 1200. However, it's an old cell, so it's working at about 50% of its original capacity. But getting 1200 milliamp hours out of this isn't too bad going. The Tanzarine cell that I'm using in my torch, that's only about 1 amp hour, and it works just fine in my torch. That lasts for plenty long enough. So you can still use this cell. This is perfectly usable. And we've got 8 of those in our battery. So if we assume that they're all in roughly the same state of health, we can still build an 8 amp hour battery out of those. So that's not bad going, really. So, okay, so we have recovered a cell, we've recharged it, and we've measured the capacity of it. So now we know what we've got and how many of them we have. We also know how we can wire them up in different combinations for different uses. So you might now say to yourself, okay, well, I've got this battery, now what do I do with it? How is any of this useful to me? Well, that's up to you, but I'll show you 2 ways that you can use recycled LiPo cells to mess around with. Number 1 is ghetto power banks like these. And if I show you a bigger example of one of those, I've got here another power bank controller that, again, I bought for £1 off of eBay. This is a dual output one. It's also got a built-in flashlight on it, but obviously that's pretty useless. And I've connected up 2 JST connectors to this. And if I take these 2 banks of 18650s, these are actually from another power bank. Not from this one, but from a different power bank. And as you can see, if I take these 2, I can combine these and I can wire them up in parallel, so we still have 3.7 volts output, but we have the combined capacity of 8 of these. So if I did that with these green ones, we'd have an 8 amp hour power bank, and that's a fairly modest capacity for a power bank. You can charge your phone up at least once or twice off of that. In this instance, these 18650s are 3 amp hours each. So do the maths, 3 amp hours times 8. We've actually got, when I wire both of these up to this power bank controller, we actually have a pretty beefy power bank on tap here. that will charge, well, it will do a lot. You know, you're looking at least, 21, 22 amp hours there. That's a lot of charge. And it's got dual output, so we can charge two things at the same time off of it. So that's one thing that we can do with these LiPos. Another thing you can do is you can turn things that are not supposed to be LiPo-powered devices into LiPo-powered devices. So I'll show you a bit of messing around with this little coin block here.